So in this video we'll discuss about the moment area method, and I'll do two type of question. One question will be just similar to the question I have done in the conjugate beam method, and another question will be a different type. So in this moment area method, to start with, let me take a simple supported beam with a point load P at the mid span. Okay, at mid span. Then the simple thing that it needs is we have to construct the M by EI diagram. So for that, the very first we need moment diagram, that is bending moment diagram. So for a simply supported beam with a point load, it is a triangular portion with a magnitude WL by 4. Okay, so if we are confused how this WL by 4 is achieved or obtained, so for this, maximum bending moment for a point load is WA into B by L. In this case, A and B are equal, that is L by 2. So W into L by 2 into L by 2 divided by L, it will be WL square. So it cancel out. So WL by 4. So this is a simple derivation of this magnitude of maximum bending moment. Now at A and B. So this is the bending moment diagram, and if we divide it by the flexural rigidity, that is EI, it will be the required M by EI diagram. Okay, the moment is positive, so the force will be acting downward in the M by EI diagram. The basic difference between moment area method and conjugate beam method starts now. Up to here we have done the same, that is M by EI diagram. But now what we have to do is we have to find out the deflected shape of the beam, and in this case the deflection will be in this mechanism, that is maximum at the point below the application of point load. So this is the deflected shape of the beam. Now from this we will determine the slope and deflection using the M by EI diagram. Now extend vertically downward from two supports and extrapolate or draw tangent from the origin of the deflected shape. So what we get is extrapolate this up to, until it get intersected at these points. Okay, so now if this is A and B, naming this A dash, B dash, and this theta A clockwise because it makes a clockwise angle with the tangent, and theta B, that is anti-clockwise because it is making a negative angle with the, or we can say anti-clockwise angle with the tangent from point B. So as I have said, to illustrate, so the very first condition is that the point load is acting at the mid span of the simply supported beam. So if we see here on application, the deflected shape, you can see it is maximum at the point load application, and this slope at point A and B, which we have to find. And from simple trigonometric relation, we know tan theta A will be equal to perpendicular, that is BB dash, and span, that is AB. So in this way we can, as we know, this is nearly a very small deflection. So for a very small theta, tan theta A will be equal to theta A, so BB dash by AB, and for theta B it will be AA dash by AB. Okay, so these are the for the deflection, for slope. Now BB dash and AA dash, AB and AB is the given span, that is L, but for BB dash what it will be the value. So for BB dash and AA dash we have to use the M by EI diagram. So considering BB dash, I am writing in language form, moment of M by EI m by ei from a to b about, I am taking out theta a, so b, okay, taking moment about b. So in m by ei diagram we have to take moment from a to b about b, then theta a, that is a bb dash, will be calculated, and ab as usual, this span, okay. And for aa dash, moment of m by ei diagram from a to b about a, okay. Deflection, for deflection of the beam, what we have to do is consider this point c dash, this point c, and this as c dash dash, okay. So we have to calculate c dash dash, okay. That is the deflection. We will understand this by doing a numerical. So up to here, c dash is equal to c dash minus c dash c, which is the required deflection. So now let's go to the numerical. So this is the question. I have done this question using conjugate beam also, conjugate beam method, and to determine the deflection at C and rotation at point A. This was the question. So the very first step is to split into two parts for the loading. So this is the given loading condition, and we can determine the reaction. This is a simply supported beam, and this loading is done at the mid span, so it will be 40 kilonewton. This will be 40 kilonewton, but in this case a little bit different. So 20 into 9 divided by 6, that gives me RB is equal to 30 kilonewton upward, and 30 minus 20, 10 kilonewton acting vertically downward, that is minus 10, so it will be acting downward 10 kilonewton, okay. So this is the given loading condition and the reaction due to the given loading. Now the next step is to draw the m by ei diagram due to the loading, taking into account of this portion AB. Due to the point loading, it will be a triangular one acting vertically downward because the moment is positive. So and the magnitude is WL by 4, that WL by 4, which is equal to 120, and taking into account of flexural rigidity, as I am drawing m by ei drawing, so as I am drawing m by ei diagram, so taking into account of ei, and the flexural rigidity for this portion is 2, so 20 ei, this will give me 60 by ei, the magnitude of this portion. Now taking into account of this 10 kilonewton acting in anticlockwise direction, so a triangular one again, okay, a triangular portion, and the magnitude is 10 into 6 minus 60, but the flexural rigidity is 2, so it will be 30 by ei acting vertically upward. And the remaining portion up to here, let me consider the left part as right part only. So 20 into 3, that is 60, and the flexural rigidity being 1, so it will be 60 kilonewton, 60 by ei acting vertically upward, okay. So this is the m by ei diagram. Now we have to draw the very first step, second step, and now third step. We have to draw the deflected shape of the beam. So consider the effect of one load at a one time, so it will be easier to determine the deflected shape. So taking into account of 80 kilonewton, this point being provided with supports, it will deflect somehow like this. Okay, and this part, okay, this free end being free to move, so it will go upward like this. I will show you with the illustration later on. Joining this point, so C dash, okay, so this part goes upward freely, and taking into account of this 20 kilonewton, now not considering this 80 kilonewton, the load or the point C will move vertically downward, and let us say this to be C dash dash, but this point B being fixed or is not allowed to move, so it will go somehow like this. As a tangent, this line will pass as a tangent for this portion. Okay, so this will be the deflected shape, and extrapolating or this point, okay, so we'll get this as B dash B, and again, as I have already mentioned earlier, we have to extrapolate this point with a tangent till it intersects at point this A dash, and this will be B dash. So A, B, this will be the slope at A, this will give the slope at B. Okay, so as I have said, to illustrate, so the very first condition is that the point load is acting at the mid span of the simply supported beam. So if we see here on application, the deflected shape, you can see it is maximum at the point load application, and you have to note this point. Okay, so you can see as we have plotted, so it goes upward from the original point. So this is the first deflected shape. Now for second case, what we said is we'll apply load at this point, so it goes down from the mean point and a deflected shape occurs in this way. So this is the illustration of the application of load. We have to find theta A, theta B, and the deflection at point C. Okay, so for that, let me determine, as I have already said, BB dash and AA dash represents the moment of M by EI diagram from A to B at respective points. So I have to find theta A, so for which theta A is equal to BB dash by AB, BB dash by AB, and BB dash is equal to moment of M by EI diagram between A and B about B, and the span length we know it is 6 meter, so 6. Moment of M by EI diagram about AB, about A, between A and B about point B. So we have to take the moment about B, for which we have 60 kilonewton or 60 by EI, so 1 by 2 into 60 by EI, span length that is 6 meter. Okay, and the loading will be at the mid span, so 6 by 2, that is 3, minus this will be acting at clockwise, it goes to the right hand side, so it will be negative, so minus 1 by 2, again a triangular portion, 30 by EI multiply by the span, that is 6, towards the base, so 1 by 3 multiply by the span, 6, so divided by 6, 1 by 2 multiply by 60 into 6 into 3 minus 1 by 2, 30 into 6 into 1 by 3, 6, divided by 6, we get 60 by EI, a positive value, and a positive value shows us a clockwise rotation, so 60 by EI is the slope or rotation at point A. That is, therefore theta A is equal to 60 by EI. Now the next problem is to determine deflection at point C. But for determining deflection at point C, we have to know the value of theta B. Okay, so with value of theta B, this value will also be theta B, and from theta B value we can find C dash C using the triangular Pythagoras relation, and again using the moment area M by A diagram we can calculate C dash dash, and subtracting from this and this we can get the value of C dash dash. Okay, so basically here we have to find C dash and C dash dash. Okay, so but very firstly we have to find theta B, which is equal to A dash by AB. So this will be now moment of M by EI diagram between A and B about A. Okay, so about A we have to find. This will be now positive as it goes to the right hand side and giving anti-clockwise moment. So 1 by 2 30 by EI multiply by the span, that is 6 meter towards the apex, so 2 by 3rd of the span length, minus 1 by 2 60 by EI multiply by 6 multiply by the point of action, that is 6 by 2, that is 3 meter, and the span is 6 meter again. So 1 by 2 multiply by 30 into 6 into 2 by 3, 6, minus 1 by 2 60 into 6 into 3 divided by 6, that is minus 30 by EI. So we have theta B here, and with theta B we can calculate C dash C. Theta B is equal to C dash C by the span length, that is BC. We have minus 30 by EI is equal to C dash C, which is to be determined, and BC is 3, so C dash C is equal to 90 by EI, minus 90 by EI. Okay, are we clear here? Then we have minus C dash C we have calculated. Now we can calculate C dash dash. Okay, this is equal to the moment of M by A diagram between B and C about C. Okay, so C dash is equal to moment of M by EI diagram about C between B and C, which is equal to, so we can calculate from B to C about C, so 1 by 2 60 EI. Make sure you are going to the right hand side, so it will be clockwise, so it will be negative, so minus 1 by 2 60 by EI multiply by the span length, that is 3 meter towards the apex, so 2 by 3 into the span length, so 1 by 2 60 into 3 into 2 by 3 into 3, we get 180, that is minus 180 by EI. Is it okay? And what we have said is the actual deflection. Okay, so the actual deflection will be equal to C dash minus C dash dash. Okay, so C dash minus C dash minus 180 by EI minus, and it will be plus, so 90 by EI This gives me minus 90 by EI, which suggests that the deflection is downward. Okay, so in this way a moment area method is applied to determine the rotation and deflection at any point in the given beam structure.